Okay, it's the fourth attempt to start recording this thing. I don't even know why I bother. You guys don't wish this. Um, so more on trig. Okay. So let's start. Let's go back to a unit circle, or just let's go back to any circle. So any circle of radius r. And take a look at the point on that circle. So the point is xy, just an arbitrary point on that circle. So the way we've been looking at these situations is that we consider an angle that is formed by the x-axis and what we call the terminal side. Let's call it theta. And then we can start discussing sine theta, cosine theta, tangent theta, and so forth. So sine of theta, cosine of theta, tangent of theta. And again, this came up before. I'm just making it official and set in stone. So if I want to consider sine theta for this specific theta, so the way we compute that, we actually kind of drop a height from that point to form a right triangle. And then this is the triangle we'll look at, and then we're going to go, okay, well, the sine is the ratio of the opposite side to hypotenuse. So what is the length of the opposite side here in this little triangle? Yeah, whatever the y coordinate is, right? The height of that point is given by the y value. And the hypotenuse is the radius of that circle. So sine theta is y over r. On the unit circle, when r equals 1, that's why sine theta is just y. The y value is the sine theta if r equals 1. Now, how about the cosine? So the cosine is the ratio of the adjacent side to the hypotenuse. So the adjacent side is this guy right here. And what gives me the length of the adjacent side? The x value, right? How far away is it along the x-axis? So the cosine theta is simply x over r, right? So again, on the unit circle, if r equals 1, cosine theta is just the x value. And tangent is irrelevant of the value of the radius. Tangent is the ratio of the opposite side to the adjacent side, so it's y over x. Is that okay? And then, of course, the other three, the cosecant theta is the reciprocal of sine, so that's r over y. The secant theta is the reciprocal of cosine, so that's r over x. And cotangent theta is the reciprocal of tangent, so it's x over y. Okay? So if I look at this circle, right, and then I look at the coordinate axis, the coordinate axis divide a plane in 4 quadrants. Do you know about that? Do you know how we count the quadrants? How do we count the quadrants? What is the first, second, third, and fourth? Yeah, counterclockwise, right? So this right here is the first quadrant. First quadrant, this is the second quadrant, this is the third quadrant, and this is the fourth quadrant. Right? So if theta is in the first quadrant, then all of my trigonometric functions are going to be positive, right? R is always positive by definition. R is the radius. Well, in the first quadrant, both x and y are going to be positive. Do you agree with that? If I take any point on that circle as long as it's in the first quadrant, both x and y value will remain positive. So therefore, sine is positive, cosine is positive, tangent is positive, cosecant, secant, and cotangent is positive, right? So all functions are positive. So I'm going to write it very small, like sine theta is greater than 0, cosine theta is greater than 0, tangent theta is greater than 0. So for any theta in the first quadrant, all those functions are going to come out positive. Now, if I keep going, if I move into the second quadrant, if I take any point in the second quadrant, the y value is positive in the second quadrant, but the x value is negative, right? So if y value is positive, then sine, since sine is y over r, sine theta will still be positive, but cosine theta will be negative, and so is tangent. Right? Since both tangent and cosine have x's in their expression, so if x is negative, the whole thing is going to be negative. If I move to the third quadrant, in third quadrant, any point in the third quadrant has a negative value for x and a negative value for y, right? So if that's the case, then both sine and cosine are going to be negative in that quadrant. So sine theta is negative, cosine theta is negative. But tangent is y over x. Both y and x are negative. So what about tangent then? Positive, right? It's negative over negative. So tangent theta will remain positive in the third quadrant. Regardless for what theta is, as long as theta is in the third quadrant, that's going to be the case. Question? Is that okay? All right. And moving on to the fourth quadrant. So how about the fourth quadrant? Y values are negative, x values are positive. Do you agree with that? Any point in the fourth quadrant will have positive x, negative y. Right? So if y is negative, then sine is negative. X is positive, so cosine is positive. And tangent is negative. Did you understand how I came up with those little inequalities? There's a cute way to remember that. I mean, I don't even think you need the cute way to remember that. You can always just judge by, what the values of the points are. But if I just focus on which functions are positive in each quadrant. So if I look at the first quadrant, which functions are positive in the first quadrant? Everything, so all. So let's call it A. How about second quadrant? What functions are positive? Sine, so let's use S. How about the third quadrant? Which functions are positive? Tangent. And the fourth quadrant, which functions are positive? Cosine. You know what that stands for? All students take calculus. That's what this means. All students take calculus. That's how you remember ASTC. All students take calculus. It's not very useful, not as good as SOHCAHTOA thingy, but because this is, you can totally figure that one out, right? If you know your ratios, you can get that. But all students take calculus will tell you which functions are positive and which functions are negative and so forth. Okay? So I want to try this example. So what is given to us is that cosine theta equals 2/5 and tangent theta is negative. Okay? So I want to find the values of other 5 trig functions. Okay? So, but what is given to me that cosine theta is 2/5. So again, I'm going to look at the circle. So the way I think of this, well, the cosine theta is x/r, right? That's what we agreed on. And what's given to me that it equals to 2/5, right? So just a wild guess, what do you think the values of x and the values of r are? 2 and 5. X is 2, r is 5. So the radius of the circle is 5, right? Well, I have two options. I can either do 2 here, right? This is the x equals 2. So the point can either end over here, right? X is 2, r is 5, or the point can end over there. X is 2, r is 5, right? So I have two options right now, but there's only one of them that's going to be correct. And this is where we use the second part of what's given. Tangent of theta is negative. So which quadrant are we in? Where cosine is positive and tangent is negative. Fourth quadrant. So this is going to be our point, right? This is where tangent is negative and cosine is positive. So this is what we look at, right? So this is our little triangle. R equals 5. The x value is 2. In order for me to find the rest of the functions, I need to know the y value. How can I find the y value here? Hypotenuse is 5. One side is 2. And we'll find the third side. Pythagorean theorem, right? By the Pythagorean theorem, the other side, so the y value, is going to be the square root of 5 squared minus 2 squared, right? So it's square root of 21. Well, plus or minus, right, if you solve it properly. Now, just because we're in the fourth quadrant, there's going to be positive square root of 21 or negative square root of 21. Negative square root of 21, right? The y values are negative there. So negative square root of 21. Does that make sense? So this was the importance of actually placing it in the proper quadrant, and this is why we needed the second piece of that problem. Otherwise, we would have two options. But that will give us a unique point where cosine is 2/5 and tangent is negative. Well, now I can go ahead and find the rest of this. Trig functions, right? So the rest will be easy. So sine theta is y over r. So that becomes negative square root of 21 over 5. I'm just taking the y value dividing by the radius. Is that okay? Tangent theta is y over x. So it's negative square root of 21 over 2. Okay? I have no idea what theta is, so it's not my problem. I'm just trying to find the other functions. And then similarly, you go for the other ones. So the secant theta, you just do the reciprocals, r over x, so that's 5/2. Cosecant theta is the reciprocal of sine, it's r over y, so it's negative 5 over the square root of 21. Is that right? Yes, I should rationalize that. Shouldn't leave radicals in the denominator, so times it by root 21 over root 21 to get negative 5 square root of 21 over 21. So this is the correct answer. I believe that my MATLAB thing will duck you for not rationalizing your denominators. It should. Okay, rationalize your denominators. And finally, cotangent. Cotangent theta is x over y. So that's negative 2 over the square root of 21. So then again, rationalize it by multiplying by the square root of 21 over square root of 21 to get negative 2 square root of 21 over 21. How's that? Any questions on this one? Does that make sense? Okay, let's try another one. So what's given to us is that cosecant theta is negative square root of 5, and theta is in fourth quadrant. So somewhere here then. So they actually gave us the way out. They told us we're in the fourth quadrant, so we need to interpret the cosecant theta. So cosecant is what over what? X or Y? It's written right there, right? Yeah. So it's R over Y, right? It's the reciprocal of sine. Okay? And that equals to negative square root of 5 over 1, right? Negative square root of 5 is negative square root of 5 over 1. So can we take wild guesses what R is and what, let's say, Y is? What is R? Yeah, so what is it right now? Well, just square root of 5. The radius is always positive, right? But the Y value is negative here. So the Y value is negative 1. Okay? So just like before, we can go ahead and find the X value, right? So the X here, because we know X squared plus Y squared equals R squared. So therefore, X would equal to plus or minus the square root of R squared minus Y squared by the Pythagorean theorem. Now, we're in the fourth quadrant, X is positive, so we're only going to take the positive value, the square root, and when I plug everything in, R squared just gives me 5 minus Y squared is just 1, so that's square root of 4, so 2. Okay? So now we can go ahead and find the rest of the functions. So let's say, well, sine is easy. Sine is the reciprocal of that one, but sine is y over r, so it's negative 1 over the square root of 5. We rationalize that, you get negative square root of 5 over 5. Right? And then I can keep going. Cosine theta is x over r, so it's 2 over the square root of 5. Is that okay? Rationalize that. Easy 2 square roots of 5 over 5. And again, I don't know what theta is, and I don't care. I don't need it. I can do the rest of them. Well, that's kind of what we did maybe like a week ago when you had to go second cosine or second sine. So we had to use inverse functions. Okay, I mean, I can do this, like, look what happens. Now, the inverse functions are very limited, but let me show you. Let's say sine theta is negative square root of 5 over 5, right? You see that? So I'm going to do this. I'm going to go square root of 5 over 5 equals that. Make it negative, right? No, I didn't make it negative. Let me try again. Square root of 5 over 5, make it negative. Here we go. And then I'll go inverse sine. So it tells me negative 26.5 degrees. So we understand what negative means. It drops this way, right? So that's what negative 22.5 degrees. Or if you go this way, it's going to be like 333.5 degrees or something like that. Okay? But again, we'll do those things a little later. I want to do a few more. Oh, the book doesn't go into the greater details of that. Yeah. Well, just convert degree into radian first. Yeah. Yeah. Or you can just, I mean, you don't even have to do that. If you want to compute, you know, if you want to compute cosine of, you know, 3 radian, just make sure your calculator is in radian mode. See? 3 cosine. So here we go. Okay? But if this was in degrees, cosine of 3 degrees, so put it in degree mode, equals that. That's cute. Cosine of 3 degrees is 0.6. Okay. I don't want to talk about this yet. Let us take a look at very basic trig equations. Okay? So solve for theta. I'm going to give you a very simple one at first. Sine theta equals 1/2. So if I go to my unit circle, and you should have it in your notes. So now I am just referring to the unit circle, 1. So sine theta equals 1/2. So is that the x or the y value? Sine is the x value or the y value? Y value. So where's the y value equaling 1/2 on the unit circle? 60 degrees, so pi over 3, right? So at this point right here, is that right? 30 degrees, right. So it's for the pi over 6 angle, right? Because we see this point, you know, whatever 1/2, and whatever is square root of 3/2, right? So just by looking at this unit circle, I can say, well, looks like the solution, theta, is pi/6. Clearly, that's not what I have. You know, mine is more of a pi/3-ish, but not drawn to scale. Or 30 degrees, depending on the units that we're using. Now, is this the only solution? No. Where is another solution? In the second quadrant, by symmetry, there is this other point, negative square root of 3/2 and 1/2. Right? Now, by symmetry, this angle right here is also pi/6, the angle between the x-axis and the terminal side. But what is the angle if you actually do it properly? What is theta here? Yeah, 120, well, 150, right? Because it's 30 degrees. No, I'm talking about the whole thing. I mean, it's always between, like, theta starts at the x-axis and then unravels. So it's either 150 or, no, you said, somebody said 5 pi/6. Yeah, it's pi minus pi/6, so it's 5 pi/6. Or theta equals 5 pi/6 or 150 degrees. Are these the only solutions? Well, I mean, if I keep going, like this point right here is going to be negative square root of 3/2 negative 1/2. Right? Well, my equation only asks for positive 1/2. And if I keep going here in this quadrant, I'll get positive square root of 3/2, but still negative 1/2. So that's not, is there only two? I can keep going. Yeah, what if I do, starting here, what if I rotate another 360 degrees? What? 390 degrees and so forth. So that's usually going to get two types of questions. They're going to say, you know, solve this equation for theta, where theta, they'll say like from 0 to 2 pi. So the theta is only in the one revolution of the circle. So then these are the only two solutions. Sometimes they'll just say, find all solutions. So we actually have to do something like this. Theta equals pi/6, but then plus a constant multiple of 2 pi, because I can go plus 2 pi, plus 4 pi, plus 6 pi. Or I can go minus 2 pi, minus 4 pi, minus 6 pi. So we usually say plus 2 pi times k, where k is just an integer. So any constant multiple of 2 pi, if you add it to pi/6, the sign of that will still be 1/2. Okay? Let me show you. If I go to my calculator, and if I'm in the radian mode, and I literally go pi/6, so blah, that's the radians, and then I'm going to add a multiple of 2 pi, let's say 17 full revolutions. So it's 17 times 2 times pi, right? So 34 pi. So plus 34 times pi, whatever. This is the radian measure. But if I take sine of that, I should get 1/2. If I don't get 1/2, we get to go home. Okay. So that doesn't matter how many revolutions, because then it's just, then I have to go relearn everything. But does that make sense? Even if we were in degrees, 30 degrees, each revolution is 360 degrees. So if I want to go 17 times around the circle, let's say negative 17 times, the other way. And let's do not 30, but 150. Let's start with that other one, okay? And then I'll go minus 17 times 360. So here we go. In degrees, and if I hit sine of that, And we don't get 1/2, we get to go home. Yeah. All right. So does that make sense? So plus 2 pi k, or depending on your measures, or 30 degrees plus 360k. So that would be all solutions, and the other solution would be 5 pi over 6 plus 2 pi k, or 150 degrees plus 360 degrees k. Is that okay? So does this make sense? How we can either find all solutions in that first revolution from 0 to 2 pi, or we can find all solutions. So then we get infinitely many solutions. Right? This represents as many as you like. They just differ by multiples of 2 pi. Okay? So functions like that have this effect that they come back to the same value after a fixed change in the variable, we call them periodic functions. So basically, the definition of a periodic function is a periodic function if there exists, I'm not going to use the fancy symbols, there exists a real number p so that f of x equals f of x plus p for all x's in a domain. I should probably be more careful and say not just plus p, but plus p times some other constant, so constant multiples of that period. So as you notice, for us, sine theta is the same as sine of theta plus 2 pi k. It doesn't matter how many multiples of 2 pi you add to your angle, the value will remain the same. Okay, so the sines are periodic functions. The simplest periodic function is a constant function, right? Just, it doesn't matter what x is, you can just say, hey, it's period of 12, and it's going to be true. But that's boring. This is the first fun periodic function. But then cosine will do the same. Cosine theta will be same as cosine theta plus 2 pi k. They're all going to be periodic, but not necessarily with a period of 2 pi. So the periods might change depending on the function. But these two will have periods of 2 pi. So let's try a few more of these equations. So is this okay? So then you just have to be careful what questions they're asking you. Just find all the solutions from 0 to 2 pi, or find all solutions. So when they say all solutions, they need the 2 pi k part. So that will actually, yeah. So again, there's going to be, you'll get two types of equations. Sometimes they'll specify an interval. Sometimes they'll just go from 0 to pi, or from like first quarter. I just care about the first quarter. I don't care about anything else. So they'll tell you the limits where theta is. So you have to make sure that your solution lands on that interval. Okay? It will. I mean, there's, or, if they don't say anything, then you assume the periodicity of the question. And of course, well, it'll get all much dirtier than this eventually. I mean, depending on the function, the period might adjust slightly. But let's just do a few more simple ones. So solve. And I just want to do all solutions. Now let's do tangent theta is square root of 3. So again, we're probably going to need that unit circle. So we know that tangent theta is y over x, right? So in order for us to get the square root of 3 out of that ratio, and if I know my unit circle very well, the only way to get that if y value is square root of 3 over 2 and the x value is 1/2. Because the ratio of those two will be square root of 3, right? So on the unit circle, do we have a point like that? Where the x is 1/2 and the y is square root of 3 over 2? Yeah, which point is that? For what theta? Yeah, 60 or pi over 3, right? So theta, just by looking at the unit circle, theta equals pi over 3, or 60 degrees. Right? Is this the only solution? But, well, before I go on, since I'm asking to find all solutions, I can say that theta is pi over 3 plus 2 pi k. That's pretty safe, right? Because this, I can rotate this way, get back to that point, it'll be the same value, or I can rotate the other way, get back to that point, it'll be the same value. So if I just keep circling the 2 pi thingy, I'm back at the same point. But what is the other value between 0 and 2 pi where the sine is square root of 3? Sine is, I'm sorry, not the sine, tangent. So tangent is positive. Which quadrants where tangent is positive? It's a first and third. So it has to be in the third quadrant. So it's actually going to be a very symmetric point. It will be negative 1/2 and a negative square root of 3 over 2. Right? So what I see is, so this is the first one. The second one, so it is pi. This is also pi over 3. By the way, we call the angles that I'm doing right now the ones that are just formed by the terminal side and the x-axis, like this angle right here. I call it the reference angle, okay? So it's pi over 3 between the terminal side and the x-axis. But the value of theta is the full rotation to that point from the original x-axis all the way there. So it's pi plus pi over 3, right? So what is that going to be? Full pi plus pi over 3. 4 pi over 3. Or in degrees is 240 degrees, right? It's 180 plus 60, right? And that one also can be circled around. So I can say theta is 4 pi over 3 plus 2 pi k, right? Do you agree with that? Well, okay, we're kind of correct, but we're not being efficient in our answer. There's one thing we don't like in math is the redundancy. We don't like the redundancy here. Because look what's going on. Certainly you notice that there is a pretty-symmetry between these 2 points, right? If I just rotate from the first point to the second point, what is the value of this rotation? pi, right? It's just a straight line. You just went pi. And then back from this point to that point, that's another pi, right? And then if I do it again, that's pi. And if I do it again, that's pi. So instead of listing these two answers, I can combine them. I can say that theta is just simply pi over 3 plus pi k. Because all I'm doing to go from one point to the other, I just need to rotate 180 degrees, so just pi, right? So I don't need to list those 2 points separately and then say they both have period of 2 pi. I can combine them into one and give it a period of pi. So tangent is a periodic function of a period pi. And that will happen every time. The 2 points going to be opposite of each other. Because again, if I look to the very front, tangents can be the same when they have the same sign. So they're either both negative or they're either both positive. So they're always going to be opposite of each other. The difference between those 2 points is going to be 180 degrees. So the period of tangent is just pi. Okay? So that takes care of all of that. So the tangent theta equals tangent of theta plus pi k. So tangent has a period of pi. Is that okay? So the reciprocal of tangent, the cotangent, will have a period of pi. The reciprocal of sine, which is cosecant, will have a period of 2 pi. The reciprocal of cosine, the secant, will have the period of 2 pi. So the period stays the same through the reciprocal. That preserves the period. Does that make sense? Kind of? Yes, no, good, bad, fun? Okay. Here's a, well, let's do another maybe fun one. How about example? How about secant theta equals negative 2 square roots of 3 over 3. Oh, I'm totally full of it. Secant theta cannot equal that. Why not? What did I write? Oh, yeah, that's totally good. Let me just do one quick computation. There's one thing we haven't talked about yet, so yeah, we're fine. All right. I want to find all solutions. Okay. So one thing we should realize, yeah, we have our definitions of secants and cosecants and all those fun points. But when we talk about secant, it's always easier to think about the cosine. Okay? So if you have an equation that involves secants, because we'll have equations that involve all of them. I mean, we're going to get all nasty and dirty with these equations. But this is simple. But so when you see secants, it's always easier to think about the cosine, because the cosine is just the reciprocal of the secant. So this equation is equivalent to solving cosine theta equals negative, the reciprocal of that, which is, well, 3 over 2 square roots of 3. But if you rationalize that, it's just negative square root of 3 over 2. So this equation is equivalent to solving the equation cosine theta equals negative square root of 3 over 2. Does that make sense? Because our brains, it's easier for us to think about sine, cosine, and tangent rather than secant, cosecant, and cotangent, because those are just reciprocals. So if we just stick with those three, and we'll be able to convert from one to the other. All right, so cosine theta negative root 3 over 2. Cosine is the x or the y value? X. So we're going to be in the second and third quadrants, right? So now, for which angle you see negative 3 this one, right? So it's negative square root of 3 over 2 and 1/2. And this one, which is negative square root of 3 over 2 and negative 1/2, right? These are the 2 points where the x value is negative root 3 over 2, right? The reference angles in both cases going to be pi over 6 and pi over 6, right? And this, again, this is what I mean by reference angle, the angle between the terminal side and the x-axis, just straight down. And then it will allow us to figure out whatever the theta equals to. Okay? So I have 2 solutions. Theta equals, so the first angle, it is pi minus pi over 6. See what I'm doing? I know the whole full half of rotation is pi, but then I need to go up pi over 6. So it's pi minus pi over 6, so that's 5 pi over 6. Are you okay with what I'm doing with that? To get all the way down, it's pi, we'll go up pi over 6. So for you, it's this way, right? Go pi, up pi over 6. So it's pi minus pi over 6. But then plus 2 pi k to find all solutions. And the other angle, I need to go full pi and then pi over 6 more. So it's pi plus pi over 6, right? So it's 7 pi over 6. Plus 2 pi k. How is that? Is that okay? Do you have any questions on this? How I'm playing with those angles? Because really all you need to know is that first quadrant on the unit circle every time, okay? The way your brain should work, you look at that first quadrant and you have those points, right? What is it? So that's root 3 over 2, 1/2, and then root 2 over 2, root 2 over 2, and then 1/2, root 3 over 2, right? And you know, pi over 6, pi over 4, pi over 3, right? Or 30, 45, 60, right? So when you look at this problem and you realize that the question is negative root 3 over 2 for the cosine, so you know we're talking about the x value. This is another connection you always need to make. X values are cosines, y values are sines. So you look at your first quadrant, where's the x value equal root 3 over 2? So that's the pi over 6, right? But you need to make it negative, so you need to jump to that side. And then you just use the symmetry. So this point is negative root 3 over 2 and 1/2, and you also have that point, which is negative root 3 over 2, negative 1/2, right? So you just need to figure out what thetas are for those 2 points. What? Yeah, but see, that will be the positive one. I don't need the positive, I only need the negative, right? Like, for example, again, solve. Well, let's do this case from 0 to 2 pi. Okay? So let's say our equation is this. Well, let's say 2 sine squared theta minus 1 equals 0. Here's a fancy little equation, right? It's a quadratic equation, really. Think about this. But if this was not sine squared, if this was just x squared, how would you go about solving this equation? Yeah. So like on this side, if I ask you to solve this equation, the first step you would do is what? Add 1 to both sides, so you get 2x squared equals 1, right? Then you would divide by 2, so x squared equals 1/2, and then you would take the square root, so x equals plus or minus square root of 1/2, right? Rationalize that, plus or minus square root of 2 over 2, right? So I'll do the same thing here. Just like I'm treating a regular polynomial equation, I'll treat this trigonometric polynomial equation. That we're really going to, eventually we're going to treat our trig functions like variables. We want to get them by itself, and then we're going to think about the meaning of the trigonometric function. I mean, right now, I don't even care that it's sine. All I know, I need to get it by itself, like over there. So I'll do the same steps. 2 sine squared theta equals 1. And then sine squared theta equals 1/2. And then sine theta equals plus or minus square root of 1/2, which is plus or minus root 2 over 2. Right? So I'm satisfied when the sine equals positive square root of 2 over 2, and I'm satisfied when the sine equals negative square root of 2 over 2, right? So I'm actually looking on my unit circle. I am happy when I'm at this point, right? Because again, the sine is the y value, root 2 over 2. I'm happy. Where else am I going to be happy? I'm happy here, right? Because the y value is negative root 2 over 2. I'm happy here. And I'm also happy here. There are 4 points where I'm going to be happy, right? This is positive root 2 over 2, positive root 2 over 2, negative root 2 over 2, negative root 2 over 2 for the sine, right? So what is this? This is pi over 4. What? The first one is pi over 4. 3 pi over 4. 5 pi over 4. 7 pi over 4. But really, what is the difference between these all 90-degree angles, right? Between pi over 4 and, what was the other one? 3 pi over 4, there's a 90 degrees. So really, the solution here is going to be really fun. It's theta equals pi over 4 plus the period of this solution is just pi over 2. It repeats itself. Pi over 2, right? So, but I mean, I'm sorry, I'll take it back. I'm actually going to write pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4. Because the question was, find the solutions from 0 to 2 pi. So those are the 4 solutions. Okay? If the question was find all solutions, then you would say theta is actually much more simpler, pi over 4 plus pi over 2k. Right? Because again, each one of those points has a period of 2 pi, but just because it's that 45-degree thing, there's an easier way to express that. So you really have to think at what your solution is and try to avoid the redundancy in your answer. Yeah, that's what I was trying to say. Does that make sense? Yeah? Try this one. I'm going to give you 2 equations to try on your own. How about, so find all solutions. Sine theta equals 1. I'm going to give you actually a few. Sine theta equals 0. cosine theta equals -1, cosine theta equals 0. So solve this 4 equations. Again, using the unit circle. I'll pause it for a minute. So for the first one, sine theta equals 1. So all you need, the y value has to equal 1. On the unit circle, what point gives you the y value equal 1? Well, that will be -1. So you only have 1 point, right? On the unit circle, there's only 1 point where the y value equals 1. Because this point right here is 1, 0, 0, 1, -1, 0, 0, -1, right? So sine is the y value equals 1 only at that point, so it's pi over 2, right? So theta equals pi over 2. That's the only time that that happens. But then period is 2 pi, so plus 2 pi k. Okay? By the way, your book writes 2k pi for some reason, doesn't it? So that's it. Does that make sense? How about sine equals 0? So the y value has to be 0. So where does that happen? At what points the y value equals 0? Yeah, the x-intercept. So that's 0 degrees, so radians, whatever. And this is pi, right? And then it's back to 0, back to pi. So you can just say it's the multiples of pi, right? The theta is actually, you can say, is just pi k. If k equals 0, you get 0. And then for any number of k, even k lends you here, odd k lends you there. This is odd k. This will be even k for that solution. Is that okay? I mean, there's no reason for us to write 0 plus 2 pi k and then pi plus 2 pi k. It's just pi k. Do you see that? It is hard to just algebraically come up with it. You just literally have to look at what's going on and try to express it in the most efficient way. Does that make sense? Kind of? How about cosine theta equals -1? Where does that happen? 180. So that's the only point, right? Because the x value is -1. So that's pi. Theta equals pi, but then plus 2 pi k. That's the only point, so the period is 2 pi on that one. Is that okay? How about the last one? Yeah, 90 and 270, or you can say it's pi over 2, then you have to go another pi, or 180, and then another 180, and another 180, right? So you can just say it's pi over 2 plus just pi k, right? The period of that solution is just pi k. Is that okay? Well, because again, for any point, if you look at this is theta, this is r. So this side is y and that side is x. So the sine is y over r. So opposite over hypotenuse. So if r equals 1, it's just sine equals y, right? So we take that and we extrapolate it to the rest of that circle. Because of course it makes no sense if you just stick to a triangle, right? Because then we're getting negatives and all that stuff. But if you just extrapolate that definition to the full rotation, you're going to get all them points. Is that okay? Because just because sine is the opposite side happens to be y over there. Well, it's y over r. Yeah, we still say that. But on the unit circle, just luckily r equals 1, so it's even simpler That's why we like the unit circle. Okay. On a not so unit circle, if r was not 1 but 7, all the points would change. Okay. But then still the ratios of y to 7 would still be the sign values. Okay. All right. Well, okay, so that's fun. So now let's consider this function. So let's just say, just for the sake of f of x equals sine of x, where x is a real number. And this is where our ability to manipulate radians becomes very important. Because radians are real numbers. Degrees are not. Degrees made up. Okay? So I can actually ask you, what is f of 0? I can ask you, what is f of pi over 6? I can ask you, what is f of pi over 4? I can ask you, what is f of pi over 3? I can ask you, what is f of pi over 2? Right? Pi over 2, pi over 3, those are all real numbers. Right? That's why we use the radians. They convert the degree measure to length. Do you remember that? The definition of the radian, what it is? It's the arc length. So that's what makes it a real number. You connect it to a distance, therefore you can drop the distance on the real number line. That's the real number, right? The definition of real number, it's on the real number line. So I can compute all of this. This is just sine of 0. According to the unit circle, that's 0, right? I can compute sine of pi over 6. According to the unit circle, that's 1/2. Right? I mean, if you reference a unit circle, you'll get all those. Sine of pi over 4, that's square root of 2 over 2. If you look at your unit circle. Sine of pi over 3, that's square root of 3 over 2. And the sine of pi over 2, that's 1. Right? So what I have here, I have a bunch of ordered pairs. 0, 0, pi over 6, 1/2, pi over 4, square root of 2 over 2, pi over 3, square root of 3 over 2, and pi over 2, 1. These are ordered pairs, right? The x and y values. If I have ordered pairs, I can plot them on the xy plane, right? I can plot these points where pi over 6 and pi over 2, those are all real numbers, so I can find them on the real number line. So if I do that, let's just hypothetically speaking say this point right here is pi. Okay? So then this point right here is pi over 2. This point right here is pi over 3. This point right here is pi over 4. This point right here is pi over 6. Because I can just divide, right? I can divide the entire pi into 3 pieces and into 6 pieces. I mean, I'm not really doing a good job at dividing them equally, but I mean, this is just some real numbers. I can find them on the number line. Well, now I can plot these points. Let's say pi over 2, if this is 1, so pi over 2, 1, I get this point. Pi over 6, 1/2, I get that point. 0, 0, I get this point. Pi over 4 and root 2 over 2, that's a little harder to compute, but I can just eyeball it. It's a little bit bigger than 1/2. For pi over 3, I get root 3 over 2, so I get something like this. So I'm getting like a little curve like that. Okay? But if I keep going, if you look at your unit circle, do I have a good unit circle in any of my? Well, think about this. The sine is the y value, right? So as you go from 0 to pi over 2, what happens to the y values? Are they increasing or decreasing? Increasing. So this is the pi over 2, you get 1. But then as you're going from pi over 2 to pi, what happens to the y values? Decreasing. And they're going to get back to 0, right? And they're decreasing at the exact same kind of point value, right? So actually I can just take that without plotting any points, and I can just say, well, it's just going to be the same thing. It's going to have that little symmetry, right? Now if I refer back to the same unit circle, if I keep rotating from pi to 3 pi over 2, the y values are increasing now, only they're negative. And they're going to get all the way to -1, right? So if I use that same logic, so this will be like, this is 2 pi, 3 pi over 2. They'll get negative and get all the way to -1 and then come back and I'll get to 0. Well, yeah, that's the equivalence in the angle measure, but we're not even going to think about degrees anymore because we want that measure to represent the length. So this is the unit circle dropped on the xy plane. That's what it looks like. Okay? Now the period is 2 pi, so it will keep repeating itself. So this is 4 pi. This is 3 pi. This is -pi. So this curve will keep repeating itself with the period of 2 pi. So this is one period of that sine curve. Okay? So sometimes now, if I ask you solve this equation, like we use the unit circle, which is totally fine. Now you can say, well, 1/2 is somewhere here, which corresponds to pi over 6. Or, if I keep going, here's another 1/2, so it corresponds to that point as well. So you get your theta equals pi over 6, and theta equals 5 pi over 6 just out of that graph. Okay? And then there's the period. Then you add 2 pi, you end up here. It's 2 pi plus pi over 6. You keep going, you end up over here. So it's 5 pi over 6 plus 2 pi. Okay, so this is that period in play. This is the 2 pi period of each solution. That's a funky little diagram. Okay? Wasn't that fun? So this is from here on. This is the graph of sine x function. Okay? I'll try to do the cosine. I'm not going to be plotting points because you kind of got the idea how we use the unit circle, I think. Here's that unit circle. So now I want to do the cosine x. F of x equals cosine x. So those are the x values, right? So if I start at 0, what is the x value here? What is the x value? 1. So the cosine will actually start at 1, right? When theta is 0, cosine is 1. And then it was going to go, as theta increases from 0 to pi over 2, what is the cosine value at pi over 2? Just basically look at the x value. What is the x value? 0, right? The x value is 0 there. So the cosine will do this. If I go, this is pi, and this is 2 pi, and this is pi over 2, and this is 3 pi over 2. Cosine will start at 1 and get all the way to 0 as you're going from 0 to pi over 2. Then as you go from pi over 2 to pi, so you're dropping the cosine, what is the value of cosine at pi? Again, you just look at the x value, -1. So it'll go all the way to -1. And then it will come back, get back to 0 as it travels this way. So it gets back to 0, and then back to 1. Right? So it will do this. Right? So there is definitely a similarity between sine curve and a cosine curve. So here's one thing which I should probably notice. It's not that big of a deal, but recall the co-function story. Do you recall the co-function story? The sine and cosine, there are co-functions, right? Sine x and cosine x are co-functions. Well, hence the co in front of cosine. Now that means what? The values of those functions is the same with respect to complementary angles. So the sine of one angle is the same as the cosine of complementary angle. Now complementary angles are the ones that add up to 90. Very good. So that means that, you know, sine of pi over 3 is the same as cosine of pi over 6. Pi over 3 and pi over 6 add up to 90 degrees, right? And what we wrote is that sine x equals cosine of pi over 2 minus x, right? So these two x and pi over 2 minus x are complementary angles. At the same time, I can say that cosine x is sine of pi over 2 minus x, right? Now, I don't know how much of that you want to be writing. I mean, whatever I just wrote is important. Now, from here on, just observe. I can rewrite the pi over 2 minus x as negative x minus pi over 2. Do you agree with that? That's the same thing? So now I'm going to try very hard to make a pretty graph. Here's me trying very hard. So here's the sine curve. Right? So this is pi over 2. This is negative pi over 2. Okay? Is that okay? One second. Let me think. That's not working out as I planned. Why is it not working? I don't think we're ready for what I'm about to show you. We're missing one little piece of information. I'm trying to think, can I do a walk around that piece of information? Oh, no, we're fine. So, okay, we're good. Now think about your transformations of graphs. Remember acrobatics of functions we talked about, all the shifts and all that fun stuff. What is the negative on the inside going to do? Flip it which way? Over the y or over the x? Over the y. So let me try if I can do this. Now to flip it over the... Oh, come on. I should have drawn it in a single pen stroke. So how does that work? So let me try to flip it. So I'm going to try to flip it over the y-axis, right? Now this is flipped. That flipped it over the x-axis, didn't it? Oh, that's really. Oh, my graph is crappy. I should be more careful. All right, I need to be really careful. I'm just going to do this, you know. Oops. That doesn't work. I do have a ruler built into this software, but so that's still crappy. So now if I try to rotate this thing, it should be like this, right? I don't know. Well, anyways, let me go back. This is not working out as planned. Use your imagination. This tells you to flip it over the y-axis, and this tells you to shift to the right by pi over 2. So picture, flip it over the y-axis and shift it to the right. Do you get the cosine curve? Yeah. So this is kind of going back to that. So you really only have a sine graph, and the cosine is just a transformation of the sine graph because of that co-function business. If you take the sine curve, you flip it over the y, and then you shift it pi over 2, you'll get the cosine curve. And that's going back to this whole co-function thing. My trick-or-treat didn't work. I needed a better graph. I need a very precise graph. Anyways, fun stuff. Good.